Okay, so this relates to section H.1, and maybe I'll write this down here, just section H.1, which is H.1. I always like to have the official title, Curves and Polar Coordinates. And what I was mentioning is yesterday I showed you how you could take a polar function, like for instance r equals cosine of 2 theta. You could take that polar function, put your TI-83, 84 calculator in polar mode, and of course make sure that your calculator is in radians, not degrees. And I showed you how you could, by picking an appropriate window where you have a beginning value of theta and an ending value of theta, and then some theta step, which I usually get quickly by taking theta max minus theta min and dividing that by 100 or whatever to get me like 100 points. But basically using the 83, 84 calculator, you can graph these polar curves quite easily. Okay, just by putting your calculator in polar mode and selecting an appropriate viewing window. But what happens is, of course, students, they like using their calculators to graph these polar curves. But what happens is then something gets a little bit lost in terms of, the understanding of these polar graphs. And so what I have here is, and ultimately to understand the connection between a trigonometric function like the cosine of 2 theta, okay, and its corresponding polar graph, which I've not drawn completely here. You have to work it out by hand. But of course, making a table of values like we saw yesterday, we had a problem where we looked at the sketch the curve with polar equation r equals 2 cosine theta. That was example 6 in the book. And that problem, we had a table of values where we picked different angles and computed different values of the radius r and then plotted the polar coordinates. But, and that's fine, but there's another way that you can, I think in a more efficient way, graph a polar equation. And what I've done here is I've graphed r equals cosine of 2 theta. My horizontal axis is theta, my vertical axis is r. So what I'm doing is r is a function of theta, and the cosine of 2 theta has a period of pi. Because the normal period of the cosine of an angle is 2 pi, so since you have a 2 there in front of the theta, right? Since you have a 2 there, since you have a 2 here, to get the period, you take 2 pi and divide by 2. And so that tells me, in a sense, how much of my trig function to graph. So r equals cosine of 2 theta does one cycle from 0 to pi. And what I've done is I've divided the 0 to pi up into, well, first I divide that interval, I cut it in half. So the halfway point is pi over 2, between 0 and pi. And then between 0 and pi over 2, the halfway point is pi over 4. And between pi over 2 and pi, the halfway point is 3 pi over 4. And then I know that those are going to be, important values for cosine of 2 theta, and I graph it. So let me give you a moment just to copy the cosine of 2 theta down, the trig function. I mean the graph here, and then we'll talk about how we can relate our trig graph to graphing the polar curve down here. All right, let me give you a moment here. Okay, so may I proceed on here? Everybody has the things copied okay? All right. So uh, so now I have, like the key values of this cosine of 2 theta function. The key values are when the angle is 0, pi over 4, pi over 2, 3 pi over 4, and pi. But from 0 to pi over 4, I can divide that by 2 and get pi over 8 and have another little value here. And if you put in pi over 8 for the theta, you're going to have the cosine of 2 times pi over 8, which is the cosine of pi over 4, which is root 2 over 2. So pi over 8 is a nice angle, and also 3 pi over 8 is a nice angle. All right, so what I do is I say, okay, let me study here the this trig function, r equals cosine of 2 theta. We start off at the angle being 0 and the radius being 1. So that's going to correspond right here to my starting point. Okay, right there. Now what happens to the radius? What happens to the radius as we move from, as the angle goes from 0 to 45 degrees, 0 to pi over 4? What happens to the radius based on the picture of the trig function? Who can chat out what's happening to the radius? Is the radius increasing or decreasing? It decreases. That's right, Robin. So that tells me then that for my polar graph, the polar graph, right, consists of a bunch of points. Okay, but the radius for each of those points, and the radius is measured from the origin, the radius is decreasing. So that means that the polar graph gets drawn back in to the origin because the radius goes from 1 to 0. So it's the radius then for every point, the radius decreases. So that causes the graph to get drawn into the origin. And when theta equals pi over 8, which is 22.5 degrees, the radius is square root of 2 over 2. So this distance here, let me see here, hold on one moment. This distance is square root of 2 over 2. Okay? And when theta equals pi over 4, so like, again, for the pi over 8 angle, when you look in the direction of 22.5 degrees, pi over 8, you move forward a distance of square root of 2 over 2, because the cosine of 2 times pi over 8 is cosine of pi over 4. That's the square root of 2 over 2. And that's how you get your coordinate there. On the other hand, when you look in the direction here of 45 degrees, when you look in that direction, okay, the theta, the radius is 0, because the trig function, the r equals cosine of 2 theta is 0 when theta is pi over 4. And so the radius is 0, and that puts you right here at the origin. Okay, so far so good. What I'm trying to do is I'm trying to trace out my curve here. Hold on, let me get that off. I'm following my trig function, and as I'm graphing the trig function, I'm graphing the polar curve at the same time. Okay, that's how we used to do it in the old days, right? And it's still important. Let me see, there's a question here. Oh yeah, okay, Robin's good. All right, so now let's look at the portion of our trig function that goes between pi over 4 and pi over 2. What happens to the radius as your angle goes from pi over 4 to pi over 2? I mean, we can see the radius is decreasing, but what else do we notice about the radius? That might be valuable. Well, is the radius positive or negative? Okay, Ryan's right. It's below the axis, so the radius is negative here. So the radius from 45 degrees to, and this is 90 degrees, right? Pi over 2. The radius is negative. And so what we do is, like, if we look at 3 pi over 8, which is 67.5 degrees, if we look along that line, okay, we look along that line there. Make that a little bit nicer. Okay, that's looking in the direction of 3 pi over 8, or 67.5 degrees. However, at 67.5 degrees, the radius here, right, this, hold on, that point there, the radius is negative. And as a matter of fact, the radius is going to equal negative square root of 2 over 2. So what you do then is you look in the direction of 67.5 degrees, or 3 pi over 8, but you go backwards a radius of, be careful here, you move backwards, because the radius is negative, a distance of square root of 2 over 2, or about 1.4. Hold the phone. Now wait. No, that's not right. 0.7, right? Square root of 2 over 2 is 0.7. Yeah. So, and there we are. So now our polar curve has to go this way. You see that? Has to go this way. And of course, at 90 degrees, okay, if you look, okay, up in the direct, well, hold on, I want green. If you look up in the direction of 90 degrees here, right? But then you go backwards 1 unit, because at 90 degrees, at pi over 2, the cosine of 2 theta is -1. And so the curve, you just continue, graphing the curve. Okay, so far are we okay? Are we okay so far with this? I mean, this is really I mean, we love our calculators, but this is really important. And it's going to be helpful for the next section too. Okay, well now, let's see here. I want to be a little bit careful here. I want to be a little bit careful. Okay, so for when theta is between pi over 2 and 3 pi over 4, what can you tell me about the radius? What can you tell me about the radius? The radius is two things. When theta goes from 90 degrees to 135 degrees, is the radius increasing or decreasing? It's increasing. That's right, Josiah. The radius is increasing, and the radius is still negative also. So what's happening is when your angle's between 90 degrees and 135 degrees, you're going to be looking in the direction of the second quadrant. So like for instance here, this value here, halfway between pi over 2 and 3 pi over 4, is 5 pi over 8. Just average the two. You know how to take an average, and you'll get 5 pi over 8. And 5 pi over 8, let me see, what would that be in terms of degrees? 5 pi over 8. That's 5 times 22.5 degrees. That, I believe, is 112.5. Okay. So if we look in the direction here of 112.5 degrees, you got to be a little careful here. Hold on, let's make that green. This is actually a really cool way to do it. Okay, this is theta. Whoops. This here is theta equals 5 pi over 8. And when the theta is 5 pi over 8, you can see, based on the graph, that the radius is negative root 2 over 2, or negative 1.7. So if you go back then, look in the direction of 112.5 degrees, but go back a distance of negative 0.707, which is negative root 2 over 2, that gets you here. And so basically, you just keep going. You keep going. And you have half the graph here. You have half the graph done. So what I did was the last part I didn't show you, right? The last part of this graph here from 0 to pi, I didn't show you this part here, just because, you know, I think, how many are feeling at least somewhat comfortable with what we're doing here? Is this helping? John's good. How many of this is this helping you? Good. Josiah, excellent. Is anybody else feeling good? Good, Robin. Good. Good. Thank you. Thank you, Francesca. Thank you, Darius. Excellent. Excellent. Thank you, Tyreek. Well, this is wonderful. It's wonderful to get this that I'm helping you feel comfortable. And you know, when we complete this part here, when we complete, you know, this part, you know, what else can the graph, what else for this fourth part of the graph, what else can it do? The graph has to do this. And notice it ends up here at this point. This point, if you look in the direction of 180 degrees, if you look in the direction of 180 degrees, okay, and move out then a radius of 1, that's going in this way, radius of 1, that gets you right at this point. Now, does anybody think they can finish the graph? So of course, what we're going to have to do, right, is to finish the graph is we have to continue the graph. We have to continue the graph and graph it, you know, all the way up to 2 pi. But can anybody maybe, starting from where we left right here, can anybody maybe finish the graph? Maybe I'll put the color in blue. Can anybody, well, I guess we can put the color in red. Can anybody finish the graph? I know you have the ability to write on the whiteboard. Do we have any volunteers? What's the rest of this polar graph r equals cosine of 2 theta look like? What does it look like? So I'll finish it, of course, but if there are any volunteers, now's your chance to finish the graph. So what I'm asking you to do is, from this point here, can you complete the graph? We've drawn half of the graph. And it's okay if you're not comfortable. I'll finish it for you. I'll give you another 10 seconds here for somebody to volunteer. So I'm not even asking you really to formally graph any more of the trig function. I mean, we have a feel for this graph now. I mean, hopefully we know what it needs to do to complete the graph. There we go. Thank you. Thank you. Excellent. Who did that? Who did that? Who was our volunteer for that? Thank you, Robin. And there you go. You've graphed a trig, you've graphed a polar equation. And, you know, a fairly interesting one, right? Now they can get like fairly complicated, right? So when they get very complicated, of course, it's nice to have the calculator to help us. But hey, you know, was this hard? This wasn't that hard, right? And hopefully you've learned a lot. So let me stop the recording on this.